This is the story of Aerolíneas Argentinas Flight 1324. We're all familiar with the 737 MAX. Even if you're not an aviation geek, you've heard about it, and you probably have strong opinions about it. The MAX crisis has been in the public eye, unlike any other crash, for quite some time. But that's not what this video is about. This video is different. On the 14th of December 2018, an Aerolíneas Argentinas Boeing 737 MAX was flying from Buenos Aires, Argentina to Punta Cana International Airport in the Dominican Republic. After takeoff, the plane climbed to its cruising altitude of 31,000 feet. While in cruise, the pilot scanned the instruments periodically to see if something was amiss. As their flight progressed, something caught their eye. Engine number 1, or the engine on the left-hand side, started acting up. The engine's vibrations were not normal. The vibrations were measured to be of 4.2. The maximum allowed was 5. The engine's vibrations were near the red line. The crew referred to the quick reference handbook and shut the erratic engine down. With one engine out, Flight 1324 could no longer maintain 31,000 feet. ATC cleared them down to 27,000 feet. Now they had to land the plane. They decided to land at Tucumán Airport. But it's not as simple as just setting up an approach and then just landing. The plane was fueled up for its flight to Punta Cana, and so was too heavy to land right away. So the pilots got down to 6,000 feet and did circuits over the airport to burn off fuel, so that they could make a safe landing. At 4 a.m. UTC, the plane landed on runway 02 of Tucumán Airport. Everyone on board survived. The funny thing is that Argentina's investigative agency found out about this incident from media reports. It turned out that no one thought to inform the investigative agency about this. Man, that must have been an awkward phone call. Once on the ground, it was clear what had caused the vibrations in the engines. Icing. The plane had flown through clouds, and it contained ice crystals and supercooled water. As the plane flew, ice accumulated on the engine spinner. The engine spinner is that conical thing in the middle of the engine. We're all familiar with how icing affects the wing of a plane, but what about the spinner? On Flight 1324, the ice on the spinner generated an imbalance. This imbalance is what led to the vibrations. So the final report for this incident was like 12 pages long, and it did not have a lot of information. But luckily for me, some very smart people have already done a ton of research on this very subject, and their findings are interesting to say the least. Now, all that's left for me to do is to regurgitate their findings and make myself sound smarter than I am. The paper is called An Experimental Study of Dynamic Ice Accretion Process on Aero Engine Spinners by Lin Kai Li and Hui Hu from the Aerospace Engineering Department of Iowa State University. If you want to go through the paper, I'll link it down in the description. The whole point of this paper is to see how the spinner shape affects ice accretion. So basically, there are three types of spinners that are used on airplanes. There's the elliptical shaped one, there's the conical shaped one, and then there's the conniptical shaped one, which is basically a combination of the first two. Each has its merits and demerits. For example, the elliptical spinner does accumulate ice at lower humidity levels, but it is aerodynamically efficient. On the other hand, the conical spinner accumulates less ice, but it's not as efficient. To test all of this out, they printed out scale models of these spinners and put them to test in an icing wind tunnel, and with that they were able to simulate the icing conditions of the atmosphere. They first identified that the spinner is more prone to icing due to its relatively low velocity. You might have this idea that icing is due to flakes of ice suspended in the air that just stick to planes as it flies along. That does happen. But in this case, supercooled water impinged on the spinner, and then it first created a thin film of water. As this film moves further towards the back of the spinner, it starts to freeze, and the ice forms in a feather-like fashion. In their test, they saw that for a conical spinner, 3/4 of its surface was covered by ice. For the elliptical and conniptical spinners, ice was observed on the forward portion of the spinner. If they changed the temperature and the humidity, they found that the icing was entirely different. For example, when the temperature was lower, the water froze immediately and it formed a layer of rough ice on the spinner. Now you might be asking yourself, why is research like this important? Research like this allows us to simulate what would happen to planes in these conditions, and that allows us to write up checklists that can help crews caught up in severe ice storms. For example, rime ice, or small rough patches of ice, is very dangerous because it is hard to detect. A while back, I did a video about a Japan Airlines cargo flight that crashed partly due to rime ice. This paper was able to measure the exact amount of rime ice that had accumulated on the spinner, and with that data, someone could calculate how that would affect the airflow into the engines. Uneven airflow into the engines can cause problems with the engine. Ice on the spinner can be very dangerous in other ways. Air Florida Flight 90 is a prime example. Ice on the spinners blocked important sensors, and that gave corrupted power data to the engines. Speaking of power, the ice affects the engine in a way that you would not expect it to. In the study, they used an electric motor to drive their scaled-down turbines, so they were able to measure the power used. They found that the conical spinner's input power went up by 237% after it was iced up. For the elliptical spinner, that number went up by a whopping 336%. So in extreme icing conditions, it is possible that the engine would not be able to deliver the power asked of it. In some circumstances, that can be catastrophic. Terrain avoidance, for example. So that's how icing affects the engines of an airplane. Up to this point, I thought that there needed to be a ton of icing for it to affect the engines of a plane, but apparently not. One thing that the report does not go into, well, there's a lot of things that this report doesn't go into, is if the engine de-icers were on. Had the de-icing system been on, it would have made this scenario a lot less likely. So, hope you learned something new about how engines ice up and the mechanism behind that. The 737 MAX is getting back into the air in a lot of places. Will you be flying on one? How confident are you in the jet on a scale of 1 to 10, with 1 being the lowest? So that's it for this video of mini air crash investigation. I know this video is a lot shorter than my usual videos, but unfortunately the final report just did not have a lot of information. Like I said, it was only like 12 pages long. But I still hope you guys enjoyed it. If you like the videos that I make, do consider liking and subscribing. It will really help the channel grow. I'll catch you guys next time. Stay safe.